Good afternoon, everyone. It's a pleasure to have Professor Wenzhen Yuan with us. Let's welcome Wenzhen back to MIT because she did her PhD back here with Ed Edelson. She did pioneering work in, tactile sensing, having high resolution tactile sensors, which many of us know about, many of us use. Prior to coming to MIT, Wenzhen was in Tsinghua. And then after she left MIT, she made a road stop in Stanford, and then was doing very nice work at CMU before finally being at UIUC. Today I'm very excited to hear about where touch sensing is because I feel like there are two camps of roboticists right now. Some of them are like, I only need vision and that's going to suffice. I definitely don't belong to that camp. I can close my eyes and do a lot. And I do think tactile is going to be a very important part of robotics. So very excited about your talk, Wenzhen. Please take it away.
Thank you very much. Thanks very much for the introduction, Phuket, and thanks very much for inviting me here. It's really a great experience to be here and like Phuket said, had a very nice time here at MIT and, from 2012 and 2018, and it's very nice to come back. So lots of the things that I'm talking about today is like actually start from my PhD time here with Ted and my colleagues here, where we start to look into the question like, how can we make robots to be able to better touch the world, understand what it touch, and have a better understanding of the world? So of course, there are like lots of challenges here to enable the robots to nicely touch the world. And definitely, we first need to have a nice sensor. And that inspired us to develop this vision-based tactile sensor gel set, which lots of you are already pretty familiar with. So in short, it's an optical-based sensors and has internal optical systems and vision to capture the change of the optics so that like finally we can use the change of the optical refractions to get fine details about contact geometry, as well as like the contact force where we can paint those black markers on the surface and track like how they move and use that to indicate if they're like some normal force or shear force and torque. So this sensor at that time is very different from other tactile sensors in the field, especially like it provides nice information about details so that we can understand lots of more information from the things. So for example, this is one of the my last conference papers when I was here. So we try to make our sensors to touch like different kind of clothes with made of different materials. And so you can see that like we can see here's lots of details about the fabrics, about the textures review from the tactile image, and we actually use that to understand the materials and understand how to deal with the materials, how to understand those materials. And this is only available with this kind of high resolution tactile sensing gel set. And for example, something we did here is like we try to ask the robot to perceive the clothes and decide how to handle them. Like, can we use a washing machine to wash that? Or no washing machine, only hand wash? And then the robot will sort the clothes and put that into different bins. And this is like a good example to show like how we perceive the objects and understand that, and even connect that with like finally a manipulation sequence that the robots can move the objects around. But of course, like there's a challenge on both sides, on perception side, but also on manipulation side. For example, like how can we grasp the objects more stably? And we definitely spent lots of effort to see that what's the connection between the tactile signal we got from gel site and will we see that like is a successful grasp or not successful grasp. So we tried lots of things, and finally we also talked with people from Berkeley, Sergey Levin. So you know that they have their specific style about like trying to look into things from data, and so that they built this system with a robot and the tactile two gel site on the side and collect lots of data, particularly so over 9,000 graspings of different graspings for grasping different objects with different outcomes, and try to develop this big network to predict whether this grasping is successful or not. So the work is pretty nice, and people really like the ideas about like using neural network to understand whether what is the consequence of this grasping process. But the thing behind the scene is that like it was actually a little bit painful process for us young people, because to collect the data we need to have those so grad students sitting in the lab watching those robots grasping objects and throw away, grasping objects, throw away, and if something goes wrong, the students need to stand up and fix it. And this will take several days. And I saw lots of you smile, so I guess you understand what that feeling is. And on my side, I actually spent lots of effort making new sensors, staying in the film, in front of the film hood, working with all those chemicals. And that was not the most pleasant memory I had for my PhD time. So we asked the question like, can we make this process less painful for young grad students? And a good solution is that like, can we use simulations? So this actually has been a long-term studies. Like for people, robotics have tried to use simulation to verify whether a system is well built or is there some problem with the system. Or of course, it's also a good platform to collect large-scale data set. But there haven't been good tools for simulating the sensors, especially for tactile sensors. And so we have been looking into that, and we decided like a good way to simulate the tactile sensors is using a data-driven methods, but we also want to make it very lightweighted. And this inspired us to develop this very lightweighted data-driven method for simulating gel set, which we call it an example-based method. So in short, what we want to do here is try to find a mapping function between the image we get here, or if we represent that as an individual pixel color here, with the shapes information, which we represent that as a surface normal values. And we assume that a polynomial function is enough, and we just want to calibrate those very small set of parameters for these polynomial functions with a few examples as shown here. And it turns out to be a very simple method, but works like pretty satisfactory. For example, here is the results of simulations of the tactile data. So we're contacting different objects, different shapes. And the thing we like the most about this simulator is that since it's simple enough, so it works very quickly. If we run the system on CPU machine, it can reach a speed of 18 frames per second if we're just making a simple setup. And it also works well for like objects with complicated geometries, and also transfer well to the new kind of sensors. For example, like this is a digit sensor developed by Meta, which has a very different and kind of challenging optics, but with a very simple calibration process. We can also easily simply simulate the response of this sensor. And after having this tool, we find that like it's a time we revisit these grasping problems, but like try to make little harm to grad students. So we try to still like train a neural network, but this time we try to collect all the data sets from the simulators, where we have this simulated robot arm grasping the simulated objects, and then transfer that to the real robots with zero shot. And the good thing is that we have this simulator text sim that looks like provides very nice information, and the data, the domain gap between the simulated data and the real sensors is pretty small. So that like it works pretty well. Like with a zero shot transfer, we can reach a 91% of successful rate for predicting whether the graph is successful or failure. So, so this is one thing we are looking into about like simulating the sensor and how it helps us to make the life easier. But another student in my lab try to look into another way for simulating the sensor. Like instead of like using data-driven methods, can we look into the basic physics of the sensors? In other words, like we try to make another visit about why gel set can provide a nice measurement about geometry. So this is a diagram about like the basic optic design behind it. So if you look at the basic part of it, it's like several components. We have light shining on the surface, where the surface is made of a deformable elastomer with a reflective coating. And the change of this elastomer surface will change the reflection finally captured by this camera. And if we want to simulate the physics, we want to like disassemble this entire sensor and try to understand the performance of optical properties of all those components of the optics here. And we hope that that can help us to simulate like what these virtual cameras can perceive. And we try to use this method that already pretty mature in computer graphic community called physics-based rendering to simulate this entire optical path. So the general ideas of this technology is that it tracks how each individual ray of the light travels in this scene. So it tries to simulate like lots of lights coming from the light source. Here is the LED. And when it hits several things, several stuff, like the lights got dissipated or reflected or deflected, moving into two different directions. But some of the light rays will finally hit the cameras and make some contribution to one particular pixels in the camera frame. So in other words, like if we can make a nice model of all the individual components, optical components in this sensor, and try to model like how they will interact with the light and finally make the lights reaching the camera display, we can simulate how these cameras will form an image when there's something change on the surface of the sensor. And the method works well, and here is a comparison about like our real sensors reading and simulated sensors, so that I can simulate like what's the response of the sensors when there's context of different objects, or if we have even a little bit different shape of the sensor. So of course, compared to our data-driven methods, we find that this fun methods, not very practical because it's much slower. Like if you need to simulate lots of light rays traveling in this scene, it takes lots of time. So you can hardly expect to collect large-scale data set of robots here. But we also value that it can provide us a lot about the insights about physics in this sensor. Especially this is an optical sensor. To make it works well, we need to model the optics well. And this tool help us to understand how the optics works, how the optics interact with each other. But on the other hand, it also gave us some thoughts about how to design a good sensor. Because since this is a physics-based simulation platform, we can actually play around with different optical components here. Like in reality, you probably want to move your light around, but in simulation, we can do that as well because it's all based on the physical components. And we can move the lights around, we can change the shape. That will become totally a new sensor design. And we see that can we use this process to help us to design the sensor? And that leads to the first topic I want to highlight for today's talk, that we want to design better sensors for robot. So why do we need to design better sensors? Because there are so many cool robots out there, and especially in recent years, robotics is gaining lots of attention worldwide, and people are inventing new robots and trying to explore new applications for different robots. And although the basic working principle of those robots are has lots of similarities, but on the configuration, on the specific design levels, they're pretty different. That also means if we're designing a sensor for each individual robots, that will be a big challenge. Especially for kind of gel-size sensors. That means for each individual new robot, each individual new kind of sensors, new kind of fingers, we need to have a totally newly designed gel-size sensors for that. So in the last 10 years, people try to explore different ways, different type of the sensors, and those sensors, you can see that lots of them are developed here by some of the excellent students here. But they are of very different shapes, different sizes, and they have different components. And each of them has a very unique optical design. And actually, it's not very easy to make those sensors good, although it takes lots of efforts, because the design process takes lots of pains. So if we want to make a good sensors, that enable robots to measure good signals, that means the sensor need to have good optical system, good optical design. And that means we need to have some expert knowledge about how the optics gel-size sensor works. And we also need to do lots of trial and errors with the real components, real prototypes, until we finally find a nice combination. And typically, it will take several months to design a new vision-based tactile sensors. And especially this process will become much harder when we are thinking about there are some robots with some challenging geometries or challenging actuation settings. And we believe this new tools about physical-based simulation platform can provide a new tools as a playground or test out our new sensor design quickly and evaluate sensor performance so that it can make the entire process much easier for designing new sensors. So the first example we're looking into that is one very challenging design cases that is for design sensors for a soft robot finger. So here demonstrate like what does it mean by like a soft robot finger. So this is a very traditional design of a pneumatic-driven soft robot fingers. So you can see that like there's a mechanical structure to make sure like when the finger is activated, when there's like air pressure into the finger bodies, it may deform in one way so that like you can grasp things in the other side. But if we're designing the sensor for this kind of robot, it will be very challenging because the entire structure is deformable. That means like if we want to mount those optical components, which are typically designed for rigid structures, it's not that easy. And also if the structure deforms, that means everything change. Like especially like a good gel set performance depends on like a good design of optical system. But if all the structure deforms, that means like everything will change. And how do you know that it's still a good optical system? And so that like considering all those cases, it's a very challenging design cases to finally obtain a robust perception results. So we try to use our tools of simulation to help us to approach the challenge and design a version of vision-based tactile sensor for this kind of robots. And here is our final solution. So we try to make these robot structures into a bellow structures so that we can have this big hollow area in the middles. And to make a gel set sensors, we need to have this reflective surface as shown here, which is attached to a transparent gel pad. And also in the back, we are using black material so that it blocks out external light. And for illumination, we use optical fibers to get the lights inside here so that the entire structure is very flexible and we are not constrained by the size of the LEDs themselves. And if the entire robot deforms, the optical fibers may deform and keep its current locations on the side of this sensing surface. And finally, we make care of like install the entire systems and put that on the robot and make a hand like this so that like it can grasp different materials. And here is examples about like the raw image we can get from the embedded cameras in the back of this deformable sensors when the robot hand is grasping an avocado. So there are lots of information that is useful here. So one is the tactile sensing, but also like the deformation may change the overall field of view of on this finger surface, and that is highly correlated with the deformable level of the finger itself. So we decide that like other than tactile sensing, another very important information we can get here is how much this finger has deformed, and we try to use that to review a very precisely estimated proprioception information. But on the design levels, there are lots of challenges we have been struggling about. For example, although this high-level design will work, but what kind of material for the surface will work the best, or how do we arrange the light, and what's the geometrics of the incoming light works the best. So we actually use the simulation-based platform to optimize our design and finally converge to a design that we're most happy about. And here shows the example process, like the most important optimization process we did is decide what color of the light we want to use. So for example, like the first one is the unoptimized one is our initial ideas. Like we want to have like good colors to cover all the areas. We probably want to alternate the colors around. But it turns out like in simulation, it didn't work well. And we tried a different bunch of combination and finally converged to the second one. And we tried to also conduct a bunch of tests of a different state of the robots, like not only in the original state that is undeformed, but also if the robot arm robot hand is a little bit deformed, will it persist original reasonable performance? So we try to develop a value metrics to evaluate like how much variance, how much information we can get from this contact information. And finally, we decide like this is the one we want to settle up with, and we made a real prototype, which is like kind of reasonably assembled the simulated one, and that come up with our that turns out to be our final optical design of the sensor. And then here shows the results about like combining our optical design with machine learning-based methods for signal processing, which help us to finally measure the surface normal of each pixels and reconstruct to get a 3D shape. So here you can see that when the robot finger is at different bending levels, we try to contact it with different shape of the objects. We can get a reasonable measurement of the contact geometry. So the other thing we have been trying to do here is proprioceptional sensing to estimate the deformation levels. So we try to simplify the signals into using only the shape of the field of view, or in other words, we try to extract this shape of the contour here and use that to train another neural network models which try to predict the deformation of a 3D point cloud that represents the full deformation of the fingers. So that means the good thing about this method is that it's didn't consider the nature of actuation of the finger, so that either the finger is deformed in an active way or passive ways. Our model can have a good estimation of the full shape of exact details of the deformation of this fingertip. And finally, this is an example of a demonstration about how the two types of sensing combine together. We can feel where we can sense both the proprioception, overall the bending levels of the robot finger, as well as the what we consider as tactile sensing, which is more informative about the surface texture. So we generally try to combine the two and try to use that to touch objects at different locations, which can provide us information about both the general deformation, general shape of the objects, as far as the local information. So this shows our initial trial about using this simulation tool to develop good sensors. And then we're thinking about whether we can turn these individual examples into a systematic frameworks for designing better sensors. And this inspired us to develop this toolbox. We named it OptiSense Studios for the aim of computer-aided sensor design for gel side or other kind of vision-based sensors. So our goal is to make this entire sim-to-real sensor optimization, design optimization pipelines, and simplify the design process so that turn that into originally several months process into a few days process. And we try to firstly model the sensors in simulation, and then render the response of the sensor, and evaluate how good the sensor is based on the render result, and based on that perform an optimization process on the sensor design. And there are several core questions through these problems other than the engineering efforts. It's more on the definition level. And one of the core questions is that, since we're making this entire physical process into a digitalized process, how can we modularize and parameterize each sensor design? And the second core question is that, once we have this design, how can we evaluate whether this is a good sensor or not that good sensor? Especially here, since we want to perform an optimization, so we want to have a quantitative evaluation rather than a very intuitive or qualitative saying that this is a good sensor or not good sensor. So here shows a demonstration of our interface where we built based on Blender, and how to model it, and how did we finally decide to modularize the sensors. So you can see that we firstly define some key optical components of the sensor, and tell our users, probably even some novice users who are not very familiar with vision-based tactile sensor, that those are the key components you need to define. And we tell them how to define it. So firstly, based on the geometry, where you can import a mesh or draw a mesh of it. And secondly, is the material you want to use, such as are you using acrylic or are you using a PDMS? There are several kinds of PDMS. They may have different refraction index. You should choose one of them. And for the coating materials, we have a bunch of libraries of materials you can choose. And finally, we need to put a camera there and a bunch of light source. You can put them around or either on the side where the light can propagate, or from the other way so the light can shine directly on the surface. And so this is a way we can finally quickly modularize the physical structures into something in this Blender interface. And the other thing we are looking into is how to quantitate quantitatively evaluate sensor. So we are looking into two things that is most essential. So one is that we want to make sure a good sensors can precisely measure the shape. And particularly for gel set, a good measurement of the shape means that you can have a good mapping correlation between the color value on each pixels with the surface normal values of the local geometry. So we try to perform like a bunch of calibration process of pressing the ball on the surface and develop two functions to evaluate like whether the sensor is doing a good job seeing being able to estimate the surface normal based on this color. So one is we call it RGB to normal function, which measures this capability based on the linearity of between the slope magnitude and this color value. And the other one we call it normative functions, which calculate the distinctiveness of color values regarding to different surface normal. And the other value metrics we want to look into a sensor is that like we want to make sure the sensor have like a less deformation of the contact geometry. For example, if a sensor is very tilted and has a very curved surface, we have camera. It's like this projection models will make the entire shape to distort a lot. That will make it pretty hard to reconstruct the original shape of the objects where we want to avoid that. So we develop two functions. One is as orthographic as possible function to make sure like the surface shall be ideally more orthogonal to the camera's sensing surface so that there's less distortion. And the other one is that we want to reduce the warping phenomena of the contact surface. And here, I would like to show two examples of the sensor optimization process we made with this new toolbox. One of the sensors we call this gel belt sensors. And the motivation of developing this sensor is that we want to be able to easily scan a large surface for industrial inspection purpose. So for this kind of task, like large-scale surface inspections, there are two requests. One is that the measurement of the shape shall be very precise. It's not only about finding that there's some texture, there's some like structure on the surface, but also being able to precisely measure that how deep is the dig or how wide is the scratch. So that means like we really need to focus a lot on the precision and possibility of like precisely reconstruct the 3D of this. And the other requirement is that like we want to make the inspection process to be very quick, so that like already in the old ideas about using tactile sensing to inspect a surface is that like you hold the sensor, press on different locations. It works well, but it's just very slow to cover the enlarged space. So we decided this rolling process instead of pressing is much a faster way to cover a large surface. So we're not the first person to use the rolling ideas, but we are probably the first person decide to use this belt, this two-wheel rolling structure to make sure the contact area is larger so that we can possibly get a more precise measurement. And here shows like how we optimize the design for a better sensing capability in a simulation. So firstly, we try to abstract the entire structures of the sensing and the optics. So here we find that the most important parts is like those light models and the acrylic, which is a rigid support, and this external layers, which is the sensing surface with reflective membrane. And we try to look into two key design factors. One is location of light. So to do this, we actually perform a forward design optimization process based on manual tuning. So this is kind of still relies on the student's wisdom to try with different ways you can put the lights, each on the side, on the top, or either other way. So it turns out to be not that straightforward. So you can see that our first intuitive design come up with some simulated result like this, which didn't provide very distinctive signals regarding to the surface normals here. And also they tried other ways, and it's much worse. And then they decide like make this pretty weird designs of this, adding this bending structure of the elastomer surface and put the light on the side in the combination. And that turns out to make a much better sensing results. So another key design factor we are looking into is a specularity level of the coating materials. And to do this, we actually perform an inverse design optimization process based on an automatic parameter searching process. So here you can see that it's our searching results. We try to define numbers for material specularities and simulated result and feed the results into our evaluation metrics, which generate the numbers. And we decide according to the curve, this is the area of the materials that can generate the best density results. And of course, in the reality, we don't really have all the possible materials. We only have several examples of the materials. So we try to choose from our material library of the coating materials that falls in this range and decide this is the final one we want to use. So after this set of optimization, it turns out our sensor actually can perform pretty nicely for reconstruct the precise results of the 3D structure. So here shows some examples. One is that a robot moving our sensors along a circuit board and measuring the local structure. And this is actually a self-driving sensor. You don't really need external robots. The sensor can run it on itself, and it feels what's the geometry of the terrain is like. And we also try to see how precise the sensor is using our plane panel. So this is a gift from our previous collaborator, Boeing, who get us a real panel from a real plane, which had lots of scratch on the surface. So our previous ideas is using a very expensive commercialized tactile sensor Gel Max, which costs about $40K, and aim at measuring very precise results about the surface geometry. And this time we use our new sensor Gel Belt. And here is a comparison. So you can see that the reconstruct 3D visually appears to be pretty similar. We also try to look into several cross sections here and draw the profile of the height. One of the lines is from this Gel Max sensors, as we consider that is ground truth. The other one is from the Gel Belt sensors, so you can see that they are pretty close. So this is one example of our optimization. Another example is we want to optimize the shape of the sensor of a curved sensor, especially one with a focus of reducing the distortion of the perception results. So here we look into the example of just this sensor called Gel Fidelity, developed by Alan. I saw you here. Very happy you're here. So it's a very nice sensor, but it's also a big challenge to design this sensor for this pretty thin and long curved structures. And you can expect there might be some inevitable distortion in the sensor itself. So we try to look into whether we can improve the shape design to make this better. So we try to, again, look into the core design. I decide those are the key geometry of the sensor. One is this sensing surface, which is a curved surface. And the other one is in the back is a mirror, and another mirror here. And we decide to parameterize this geometry based on the caging methods. In other words, we try to define this cage of this each curved surface with those 9 key points, and manually define where is the boundary of the parameter search we want to search around. And then we search around all the shape within the boundaries and generate this optimized shape for the sensor. And here shows the final results as a comparison of the original design, the optimized design with the simulated performance and the real performance. And we demonstrate here by pushing a Lego blocks somewhere a little bit closer to the tip of the sensor. So you can see that for the original sensor, there's lots of distortion, so that although the Lego geometry is round, but here it's not round anymore, it's pretty elliptical. But after our optimization using the new shape, the view we can get from the camera is much more close to the real shape of the Lego block. Okay, that summarizes our efforts on using new way to design the sensor and understand how to evolve to get a better sensor. So before I proceed to the next section, so I wonder any questions so far?
How fast is the simulation?
Oh, good question. So as I said, at first when we try to work with large-scale data collections, we use a data-driven method. So this one works very fast and actually very practical for large-scale data collections. Before any optimization, we can run that with a speed of 20 hertz. But for the physical-based methods for each rendering. I think it takes like if we tune all the resolution to the max, it's about like 20 minutes, 30 minutes for one frame.
And when you're doing the optimization, are you using the physics-based?
Yeah. Yes. So the data point is actually much smaller. So usually, like, I think we can just search a scale of several tens or 100 to 100 frames. That's kind of good enough to give us a good parameter.
And then how do you choose what frames to simulate?
Oh, that's a good question. So I would say that like at this stage, there's still lots of human wisdom involved here. So firstly, we need a human to start with like some initial design of the sensor, general shape you want to have, and also like we rely on humans to decide like which are the parameters you want to optimize. So like based on that, like we do a parameter search within the range of this definition. Well, so that is our efforts for building better sensors. And the other topics I want to cover today is our efforts for looking into how to use tactile sensors to better perceive the physical world and help robots to better interact with those physical objects, especially in pretty challenging settings. So there are lots of contexts when we say that the physical world is challenging and very hard to interact with. So I'm taking an example of like something you can find in a kitchen cabinet. So you can see that like there are lots of like particle materials and lots of sauce there, like ketchup, mustard. And as a human, you can see that, like, you know that, like, if you pour them, they will flow down. But sometimes you will make a mess, right? Because they're pretty sticky and have very complicated physical properties. So we try to look into, like, whether we can get a good understanding of physical properties of those, like, very complicated materials like liquids. So we got the inspiration from the humans. Like we found that like if a human target at perceiving the physical properties of some liquids, for example in bottles, a natural thing is that like we will shake the bottle and we can feel lots of vibration. And based on that, we can understand some information such as like what kind of liquid it is inside the bottle and how much liquid there is. And actually, people have been looking into doing the similar things with a robot, like shaking the bottle, feel the vibration, and use that to classify what kind of what kind of liquid it is. But we want to learn. We want to learn more. We want to get a deeper understanding about like how this vibration pattern is connected to the properties of this liquid. So to do this, we try to make the things simpler. We try to look like what we consider a simplest shaking, which just push the liquid from one side to the other side, which may stimulate lots of vibration patterns of the liquids inside the bottle. And these vibration patterns may be very different according to the liquids, especially for the sticky liquids, the vibrations will be like much flatter than the other ones. So we try to ask the robot to do the similar things, do a simple vibration, simple stimulations and measuring those vibration patterns with gel side. It turns out it works pretty well. So we can measure the shear force with a very large sensitivities. So you can see those vibration patterns with the liquids when tracking the motion of the markers. So we actually further reduce the dimensionality of this into a 1D, just kind of look at how this temporarily change. And it turns out to be like very, very close to the damping signal. And we try to make it even simpler by further reduce the dimensionality of these vibration patterns with two parameters. One is the decay rate of these vibration signals, and the other one is the frequency. And it turns out, like even in this case, those two parameters can make a big distinction between different kind of liquids. If we're looking again into water, oil, detergent, so you can see that their patterns look different. And if we look at the numbers, they're more different. Especially like if we're trying a lot of them, like they're very distinctive from each other. And we can easily like classify the type of liquids from one to each other. But there's another question. You may find that's an interesting thing, like why the distribution of the data is like along a line instead of like stick around the round area, right? So that is actually because we're trying to diverse our data set by adding different amount of liquids in the water. And it turns out if we track along this principal axis of the distribution of the data, they align pretty well with the volume of the liquid. So that inspires us to think like, can we get a more precise measurement of those properties rather than just like a qualitative classification. So this time, my student looked into like a more challenging case. Like we try to put lots of sugars in the water, but we try to control the different amount of sugar from 0% to 160%. So visually, they are almost the same to humans. And if a human receives this, pretty likely you will say that like they are almost the same. Of course, if you taste it, they are very different. But the small difference based on like the amount of sugar in the water actually can cause some difference in the vibration patterns that can be precisely captured by tactile data. And here again, we try to get those two key parameters, the decay rate of the vibrations and the frequencies. And they align pretty well, distributed pretty well according to the height of the liquids and the sugar concentration level, which is actually also almost linear correlated to the viscosity levels here. So you can see that like they distribute pretty well so that we can easily fit a surface based on the data. And based on that, we can easily predict like what's the amount of liquids in the bottles and what's the amount of sugar in the solvents. And this prediction, although it's not perfect, but we did some informal tests with human, and we believe that it's much, much better than what human can do. And we also find that the model is actually pretty generative. So here we actually firstly try 3 different kind of materials: olive oil, corn oil, marine, and they have different viscosity level from the sugar water. And here, but we directly try to see their alignment with the model we get from the sugar water, and see that like they are reasonably aligned on this model. Another question we ask is that like, what if we have different type of bottle? For example, if we have like a glass bottle versus a plastic bottle, or a bottle with like different size. Of course, it turns out the model shape has changed a lot, but it turns out like we can easily calibrate the change of these models based on only a few data sets. So that like after you collect a few data sets, change the shape of your model, you can well estimate the viscosity or level of sugars in this new kind of bottle. And this helps us to get a good understanding about property of the liquids in a bottle. Then we question about like how this can help us or help a robot to do a better job in a kitchen. So we look into lots of the funny things robots can do, humans do with the liquids in the kitchen. And found that like one of the very interesting and challenging things humans trying to do is garnishing a dish with different sauce. So this is actually we consider is a pretty delicate and challenging manipulation task where you slowly squeeze the bottles and make sure like the sauce you squeeze out can follow a very consistent patterns or even some well-controlled patterns. And this is especially challenging is because like those salts are always highly viscous, and it's very hard to predict like what's the performance of them they are. So we try to build this entire loop between like perception and manipulation. Like firstly perceive the liquids, understand their property, and then understand how to connect that with the strategy of manipulation. And so this shows like our entire system is what the entire system is like. So you can see that our robot firstly grabs a bottle, squeeze bottle with some sauce. Actually, the robot has no knowledge about this sauce before. And then it shakes it a little bit, collects some haptic signals, actually based on the first torque sensor here, and decide what's the best way to squeeze the sauce. And then follow our predefined drawing patterns to draw some patterns on this plate. So these two sauces actually they're pretty different. If you look at how the robot do them, they also do it differently. Like for the second one with I think this is sriracha, is some hot sauce. The robot actually move it much faster. But finally, the pattern, if you look at the patterns, the two drawings with the two sauces, actually they have like a very similar width and consistent width. And to do this, we actually built these new models that for machine learning with the machine learning methods. So the input here is the first torque signals we got when rotating the sauce. It's a vibration signal, again, contains lots of information about the fluid properties. And then we try to connect that with the learning structure and output is something parameter relevant to the manipulation sequence rather than an explicit representation of the properties. So particular here is connect that with the expectation about the flow rate of the sauce under squeezing motions, and also our expectation of the stacking patterns of this liquid And once we have that, we try to use that to control the robots, to use different speeds for squeezing the sauce, and try to make sure it can make a consistent stroke of it. So this is actually much harder to do than saying that, because like at first we may think that like if you just squeeze your bottle with a consistent speed or with some like other feedback, like some weak feedback, can you do a similar thing? And here is we are doing a comparison between our method with some like a more straightforward method. And you can see that actually those straightforward methods didn't work as well as you expected, because the performance of those viscous liquid is so complicated. So sometimes it's unexpectedly, like it makes a like very big dot at the beginning, or sometimes it goes like thicker and thicker when you draw it. And this is another example. It's a maple syrup. It's actually very much less viscous, kind of similar to water, but still like more viscous than water. So in this case, like if you don't pay lots of attention, very easily like you can get a big drop of it. So that will ruin your entire drawing. But with our method, like we try to firstly perceive the liquid and estimate like what is the expected performance of the liquid manipulation, and finally we can get a very nice stroke, which with a consistent width and very close to our target width. And here are some examples of our robots drawing things, like with one kind of sauce but different target width, or with multiple sauce, where you definitely need to make sure your policy is consistent so that like you can make them of like the same width. And we also look into another similar settings where we want to make pancakes. But we want the robot to be smarter than humans, like making a manually defined shape of a pancake instead of just a round pancake. And this becomes a similar question that like we want to make the dispense process to be controllable and make a very consistent and controllable stroke from the pancake batter. And we again firstly perform an exploration process. Here we try to use a wrist to push into the batter and measure what's the impedance force in this process. Especially we are pushing at different width here. And based on that, we try to decide like what is a nice speed for pouring the batter out from this bowl so that we can make a consistent stroke. Okay. I think I will just stop here and make a summary of today's talk. So as the target title indicates, I'm trying to do two things. So one is to design better tactile sensors. And to do this, we try to develop an optimization process that is based on a physical-based simulation platform. And this platform enables us to play around different optical components in a vision-based tactile sensor like toy blocks, so that we can easily assemble new sensors. And after that, we develop evaluation metrics to evaluate how good the sensor is and optimize the parameters. And finally, that can show that like it helps a lot for us to design sensors for soft fingers and also sensors for precisely inspecting large-scale surface. And I also show our efforts on exploring new ways for robots to using haptic perceptions to understand the physical world. And today I showed the examples of perceiving the physical properties of liquids or shakings. And we found that through a modeling of these vibration patterns, we can estimate like both the volume and as well as the viscosity level of the liquids in the bottle, and we can even connect that with some manipulation primitives to precisely control the liquid dispensing and making some beautiful patterns. So at last, I would also like to thank all my students who are I think they are heroes behind the scenes, like came up with all the excellent ideas and finally carry out these challenging projects and make everything you've seen today. And thank you for listening.
So we have time for a few questions. Yeah.
Thank you for the talk. It was very enlightening. I appreciate you coming. I had a question about this last slide we talked about, sort of like perception and the exploration phase.
Mm-hmm.
Could you describe more about what is actually occurring in that exploration phase? Is this reinforcement learning? Could you just maybe describe more in detail there?
That's a good question. So we try to, I guess you're referring to this one, right? We're not trying to do a more complicated manipulation sequence, but we are rather just controlling the speed of dispense. Particularly here, we find that there are two factors that will influence our dispensing of the liquid. One is how fast are you squeezing the bottle, and the other one is how fast you're moving. So the two of them actually works collaboratively, and we decided to fix the squeezing speed, but only change the speed we are moving around to make sure it can form a consistent stroke. And to do that, so we're trying to consider two sequences here. So one is the flow rate, if we're keeping this consistent squeezing motions, what's the flow rate of the liquid? And the other one is the stacking pattern. That means the same amount, the connection between the volume of the fluid and how thick it will spread on the surface. And after these two, so we can actually do a simple calculation and get the inverse calculation and calculate what is the target speed for the robot to move.
More questions? In the back? The microphone.
Thank you for the talk. Does this work only on a single kind of surface? Just thinking when I'm cooking, if I put eggs on a hot pan versus a cold pan, it's very different.
That's a great question. So that is another limitation of our work at this moment. So you can see that we're trying to model in two things. One is flow rate is based on the squeeze bottle itself, and the other one is stacking patterns, whether the liquids will build up very high or spread out pretty thin. So this may depend on two things. One is the liquid itself, the other one is property of the surface. So I think we only demonstrate that this entire loop will work, and it will work well for simple scenarios. But if we expand that more, as far as we can connect these patterns with the property of the surface we are targeted at dispensing, I think this problem will have a more easy to generalizable.
Thank you. I guess I've got another one then. You mentioned that the physics-based rendering was just very slow. What's driving that? Is the physics very complicated, or can you say more about that?
So it's the computational process is kind of hard. So the way it does is to track, I don't have the animation anymore, but it's tracking individual light ray. So it's a geometrical process. You need to calculate which surface it hits, and using a BRDI function to calculate the distribution of the outgoing light. So that will take time, especially finally to simulate the entire scene and forming an image with less noise. You need to track lots of light ray here. So that adds up to lots of computational requests.
Thank you.
So maybe one question from my side. So I think all these optical sensors are great and they can measure a lot of things. Sometimes I wonder if we are measuring too much. There are so many touch sensors out there, right?
Good question.
Maybe measure too little.
Good question.
The question is how much do we need, and
that's a good question. Yeah, we actually had a discussion about this at the VTech workshop at ICRA this year. I guess it's a lot of time. And sensing people are very excited about getting those nice information. Definitely it's nice. It's always nice you have lots of information. And I didn't speak because I feel I probably is the most negative person in the room. Feel that we don't necessarily need this high resolution tactile sensing. So I think it comes from two sides. One is that from the application side, for one particular application, what is a good enough sensor, especially if we can parameterize it as. On the other side is the sensor design side. As I said, we actually spend lots of effort to design those evaluation metrics and use that to decide what is the sensor we want. And currently our evaluation metrics try to focus on making sensor as precise as possible, But we also actually have lots of discussion with my students. Like we probably want to consider the real application cases. For example, if our target is just detect contact versus no context, probably we can use a simple evaluation matrix so that like we believe like if we combine that with our optimization process, we can come up with like low cost yet high score sensor.
Okay, great. So let's thank our speaker once again for the wonderful talk. And this is our present from the
Thank you.
robotics seminar.
Thank you very much.
And there'll be a reception outside, so please join us for the reception.